Hello class, let's continue on with chapter 3, the second part of chapter 3 and problems related to all the theory that I covered in my last recording. So we start off with this section called differential length, area and volume. I'm sure you remember all the stuff that we did where in the three systems, Cartesian or rectangular, cylindrical and spherical, we defined differential length, and then we defined differential area, surface area and differential volume, and for each of these we saw formulas on how to set these equations up, and then I promised you that we would integrate to find the length or the area or the volume of a certain surface or object. Okay, so I'm moving on to the first slide where we will look at a problem or an example in this case. So I stopped on slide 56, and slide 56 is example 3-4 from our textbook. It's on page 144. So here you will see the first example of why we defined all these differential areas or differential items, length, area and volume, and how to use it. So here you can see in this drawing that a certain area, and it's not a rectangular area, it's actually curved. So how to find the area of the cylindrical surface? This is a cylindrical surface, it's part of a cylinder. So imagine a cylinder, and this is one piece of it, and in here certain factors, certain properties have been given. R equals 5, z goes from 0 to 3 in that direction, which is 0 to 3, and phi, this angle, as you may remember, goes from 30 to 60. Okay, so pretty simple example. I don't want to spend too much time. So what we do is, in solving all these kinds of problems, you use one of the definitions of the differentials, either length or area or volume. In this case we pick this differential area ds, dsr in particular, right? And so that is defined as this. Previously we have defined this. So in the unit direction r, which is obviously in this direction, right, coming out, r unit vector is then the coefficient is r d phi dz. Okay, so that is the definition, and from there to find the scalar area you actually integrate. So I will let you look through this. It's a solved example, so it should be pretty easy to follow. The one thing that I wanted to show, because it wasn't done too clearly in the example, is when you run into this double integral. So we're going to do double integrals, triple integrals in this section and in the future of this course. So how to do this? Maybe you know this very well, I'm wasting my time, but maybe you don't. So I thought I'd at least spend some time to do this. So see how you set this up, and then you actually shift the order of d phi dz to dz d phi. Then why did I do this? I have another slide, and I tell you, see next slide, where I try to give you a clear demonstration or a clear explanation of how to do double integrals. Now this is not this problem, right? This is just an example, but I want to show you how to do a double integral. So first you integrate this with respect to x, assuming y is a constant. Then you get some fixed quantity. Then you integrate the outside, which is with respect to y dy, and the limits of y to 0 to 1 of the whatever you found inside. So it's a two-step process. I'm sure you've done it in math, but I wanted to show you an example because we'll be doing a lot of this in this section. So follow along the steps and make sure you understand how to do a double integral, and the same rule applies to a triple or volume integral. Okay? So once you know how to do that, then the answer to this problem in the textbook comes out to be 5 pi by 2, and you can see I think he does it slightly differently. You can, if you know that method, you can do that. If you want to learn my method here, which is actually in my opinion more useful, learn this method and you'll get the same 5 pi by 2. Okay. All right, I'm going to move on to the next example, and this is next problem, and this is also an example. This is example 3.5 on page 146 in your textbook. And here we are given again a piece of a sphere in this case, right? The sphere as a center at the origin, and only this piece of this whole sphere we need to find the area, right? So same approach. You first, now this is in spherical coordinates, right? Previous problem was cylindrical, this is spherical coordinates. Here also see how the three fact parameters are theta and phi, right? We have r, theta and phi in a cylindrical system as I show you here. So r is this point or direction or magnitude of the radius of the football from the center to the tip. So that is r. Actually he shows small r, but in our case we use big R. This is from a different textbook. So r is a factor. Then we have phi, which is this angle along from the x-axis. So that is shown to be, that is all around. So it's 0 to 360 degrees. And then we have this other angle theta, which is shown here, right? So that is where the angle of this r with the z-axis, that's theta. So theta is given to be either 30 or 60. So it goes between 30 and 60, which is what is shown here. So given this, how do you solve to find this? So first you set up this, or you pick the right equation, the area equation, the differential area. Once you have this, then he shows you in the example. I'll let you read through it. This is also a double integral because it's also an area. So you can see the method he's used, or you can use the method I just showed you, and you should be able to get about 20.7 centimeters square. Assuming, yeah, this is given to be 3 centimeters. So the area of this whole surface comes out to be 20.7. So take a good look at the example in the textbook. Make sure you understand the logic. Don't move ahead without understanding, because much of the future stuff is going to depend on your understanding this example that we just walked through, example 3.3-5, thoroughly, completely. Okay. All right. Next, I have a problem from the back of the textbook, from the back of the chapter, and this is problem 325. So here, let's look at the problem. Here, this drawing I just picked from our notes. He doesn't actually give you any drawing in this, and there's actually many sections A, B, C, D, E. I just picked E to solve with you here, and I'll show you what the problem is. So use the appropriate expression for the differential surface area ds, right, which is what we have been doing in the last two examples. So pick the right ds, and then for this surface, now he has just given you r, he has given you theta, and he has given you phi, which means this is part of a cylinder, right? So by looking at what has been given, you can guess whether it's a cylinder or a sphere, or you have to use the rectangular coordinates. So based on that, you then pick the right formula from what we have already learned, and then you apply the integration to solve and determine the area of each of these surfaces. So I guess what I'm trying to say is sometimes you have to sketch it to understand how to solve a problem. Sometimes you blindly apply a formula and it works, it might work. So let me go to example 325, sorry, yeah, here it is, 325 in our textbook. So it is a cone. I've drawn it. Actually, sometimes they tell you you have to, yeah, also sketch the outline of the surface. That means he wants us to sketch it. So that's why I had to sketch it here. All right. So based on the fact that theta is a constant, pi by 3, which is 180 by 3 or 60, that means this angle is a constant, right? So that is only possible if it's a cone in the spherical system. So this is part of a sphere, and the cone has a bottom and it has this opening or mouth on the top. So theta is 60 degrees. Radius goes from 0 to 5. That means this goes from 0 at the bottom to 5 at the top, right? 5. And then obviously the other dimension, which is phi, the angle, is a complete 360. That means you're going all around, right? So given these three pieces of information, this is how you sketch it, and then you apply the formula to find the right area. So here, because theta is fixed, so we use the formula for the conical surface, which is this from our notes. So ds theta is theta times r sine theta dr d phi, where this theta is obviously the unit vector, and this r is in this direction, right, going out. The unit vector is going out. Actually, we are picking ds theta because we want to find theta is in this direction, right? So that is fixed. So whatever is fixed is what you pick. So if theta is in this direction, then your vector is coming out like this. Again, this vector, if I draw a line, it will be coming out like this, right? Coming out. So that is what is the unit vector. Okay. So to find the complete area of the cone, always remember one factor of the three will be a fixed value, and that fixed value is the unit vector defining which of these surface differential area formulas you're going to pick. Okay, I hope that makes sense. As we do more problems, you may get a better handle. So picking this, now the area is the integral of this, right, where theta is fixed in this formula. So this is what you write here, and you have to set up the limits appropriately given what we know. We know that the radius goes from 0 at the bottom of the cone to 5 at the mouth, and we know phi is a full 0 to 360. So you set these limits up, then you write this formula. This theta we know is going to be pi by 3. So I could have just done sine theta of 60 and written it, but anyway, this is how it shows in the textbook many times. So if you do that, you get this formula. Once you integrate, you get 21.6 pi. Okay. All right. So that was one example of, and there's many more. I'll probably give you some homework on how to do this. Here is another problem. This time we are moving into volumes. So the last three problems we saw, two examples and a problem, had to do with area, right? So we picked the right formula for the differential, and then we applied the limits and integrated. Here we have to find a volume. So again, a surface is given, certain data is given for r, phi and z. So if r, phi and z is given, you know that this is a cylinder or a part of a cylinder. So given that a part of the cylinder with this information, then sketch the outline of this volume and then apply this formula and then integrate, right? So that is how you solve it. So I showed you this just to remind you that we are part of a cylinder. So let's see how to solve this. Okay, so this is problem 326. Now the cylinder or the part of the cylinder looks like this. So if you look at how I got this, look at the three properties that are given. We are given that r, the radius, is from 2 to 5, right? So if this is the radius axis along the y-axis, right? You can see that here also. R is always this direction along the this axis, right? So R goes from 2 to 5. So 2 to 5, right? Not along the y-axis, but in this direction, and it hits the y-axis here. So I'm using that conveniently, and then phi is pi by 2 to pi. That's why I started the wall, the Great Wall of China, right here, because phi, which is measured from the x-axis, the lowest value of phi is 90. So that is, so starting from the x-axis, the first time you hit 90 is at the y-axis, and then it goes to pi, which is the z-axis, right? 180 degrees. I mean, not the z, but if you keep going, actually I think it should stop here where the negative x-axis is. So maybe this is a mistake. I shouldn't have drawn it here. I should have stopped here, the back of the x-axis, right? So this portion I should not have included. So anyway, not a terrible mistake. The other factor we are given is that the z dimension goes from 0 to t to 2. So z is in this direction, right? Up. So z equals 0 is the bottom, z equals 2 is this. So this section, let's see if I can draw a quick line. Yeah. Yeah, I think this wall should cut off at the red line, not go beyond. Okay, sorry about that. Anyway, so how do you solve? So the volume formula is pretty simple for a cylinder, R dr d phi dz. So set that up. Now there is no direction to worry about, so there's only one formula, right? Unlike the surface area, the area formulas where we had to find a unit vector also. Here we don't have to worry about that. There's only one formula, there's three limits. You apply that and you do a triple integration, and actually I have shown you each step. So first you start with the inside dr, then the next integral is the d phi, next integral dz. So follow along if you have the time and the interest. This will be good for you to see how exactly I come up with the final answer, which is 10 into phi pi. Okay, all right. And also see how you define the surface and so on. Okay, problem 326. Okay, next. Okay, you just finished 326. Hold on, I might need to take a break here. Okay, so let me skip ahead to the next problem, and this problem is on line integrals. Okay, so this problem is not from our textbook, but we need to know how to do this. There are some other problems in our textbook which will depend on this knowledge. So I thought I would give you at least one example each of the line integral, the surface integral, and the volume integral. Okay. All right. So what does this problem state or ask us to do? So we are given a vector field A equals, and here this problem, this textbook is using I, J, K, which is nothing but our x, y, z. So don't get too confused. And this is in Cartesian coordinates, as you can tell. So A is given like this, and we have to evaluate the line integral on the closed surface or the closed path C of this scalar quantity A dot dr, right? That's the line integral. Now what is this closed path? It is given two ways, A and B. In A or B is easier to understand. So we have to go from 0, 0, 0 to 1, 1, 1, right? This is a three-dimensional system. So the first point is the origin, and the second point of this traveling is 1, 1, 1. But instead of going straight, he wants us to do this. He wants us to go 0, 0, 0 to 1, 0, 0, which is here along the x-axis. Then from here he wants us to go to 1, 1, 0, which is here along the y parallel to the y-axis, and then he wants us to climb up on the z-axis to 1, 1, 1. So this is a path to follow. Okay, so you'll see many problems like this where they give you a particular way to travel. That's one way. The other way is a more complex way. Here he has given us kind of a equation for a curve, right? X is equal to t, y is equal to t square, z equals to t cube. These are again parametric equations that define a certain path or a curve, and you can sketch this, maybe put it into MATLAB and see what it comes up with. I haven't done that, but we don't need to know the exact thing. All we know is that by using this these parametric equations, we can still solve the problem, knowing that we have to go from here to here. Okay, so how to solve these two sections, A and B? So one thing that I have given you as background information before we look at solving the problem. So let's look at this portion first. So we need both A and dr, right? A is given. What is dr? Dr is like a differential length vector, right? You remember that. We call it dr or dl. So dr is the sum of dxi, dyj and dzk along the three axes. This is by definition, and we have learned this already in our earlier sections on differential elements. Now another way that we have also learned, and this is more useful for part A, this is useful to solve part B, but for part A you have to think of the vector or the path r, the distance, the traveling path, as the sum of three three parametric equations, x, the y and the z, each attached to one unit vector. So you have to write the travel like this. X and t is a function of time, right? So the three given parametric coefficients are written in this way. Then you can create dr, right? Dr by dt is this, right? So remember this and this as we solve part A and part B. Okay, all right. So let me go to the solution, and here it is. So A is given, right? And R also is xt I plus yt j plus zt k. So we know how to create these, right? We are just copying whatever is given here. Now for part A, like I said, we are given x equals t, y equals t square, z equals t cube. So R, which is this equation, xt you put this t, y as a function of t you put t square, z as a function of t you given t cube, so put that, then you get dr by dt. You can take a differentiation of each of these elements, and remember t is the independent variable here. Then you write dr as just move the dt over to the other side, right? So now you have set up, you have a. Now a also is given in x and y, right? So you have to substitute these x and y's into the equation for a. So you have a in terms of t and you have dr in terms of t, where t is the independent variable. Lastly, you have to take the points that are given to us 0, 0, 0 and 1, 1, 1 and also translate them into t equals 0 and t equals 1. So how do you get that? So put t equals 0, you get each of these is 0. Put t equals 1, each of these is 1, right? So that tells you that t equals 0 corresponds to this, t equals 1 corresponds to this, and since we are setting up our equation in terms of t, the limits now become in t as 0 and 1. Okay, so you solve this, you get a nice round number 5. So that was part A. Part B, now we have 3 sections of travel, right? Like I showed you here, there is section line 1, line 2, line 3. So for each of these sections of travel, you have to define certain values so that you can then apply the equation, you know, a dr, which actually consists now of 3 integrals, each for each section, line 1, line 2, line 3. And also, as you look at these, you can say, for example, in this path, there is only movement on the x-axis from the point 0 to the point 1 on the x-axis. On the y and the z-axis, you are doing no travel, right? So then we say delta or dy and dz are 0, dz goes from 0 to 1. So z's limits in the integration are, dx goes from 0 to 1. So the limits for integration on the x side is 0 to 1. Okay. So using those properties which I have written here, dx is 1, x goes from 0 to 1, dy is 0, dz is 0 for path A. Similarly, path B, path C, then you can write dr as the sum of all that. So a dr now becomes a times this, right? And it's if you have to take a scalar product, you just multiply these two, right? You drop the ijk unit vectors. So with that, you come up with this for a dot dr. Now this consists of 3 sections, right? One for each path. So the 3 sections apply the appropriate limit. So for line 1, you get you apply these limits, you get the integral to be 1. Line 2, you get to be 0. Line 3, you get to be 20 by 3. So adding, you get 23 by 3. Okay. So I hope this helps. Take a few minutes to understand how this is done, and if you have any questions, let me know. Next, I have a problem on surface integral. This also is not from our textbook, but this is a useful concept. You need to know this. So we are given a field, right, G, and here we are asked to, whenever they say flux, you know that's talking about a surface integral, right? So the flux is in everywhere, and we are asked to find the flux out of the entire surface S of the cylinder given by r equals 1, so the radius is 1, and z lies between 0 and 1. So z is in this direction, so 0 and 1. Okay. So also note that phi, now this is cylindrical, so go back and look at your cylindrical drawings where phi is a factor, right? And phi goes from 0 to 2 pi, which means it covers the whole circle. Okay. So given this question, we now solve something called the flux or the surface integral. So G is given. Now phi again consists of 3 paths. It's actually this integral, right, of the area, but it consists of phi top, psi, actually this is psi top, psi bottom, psi side, right? which are the three sides. There's a top side, there's a side side, and there's a bottom side. Okay, so you have to divide it into three parts, and for each of these areas or for each of these psi calculation, you have to pick the right differential area formula. So here's one, here's second, here's the third. Now the top and the bottom are really the same, except the unit vector is in the reverse direction. Okay, the side, of course, we use this. So using this, then you calculate, you write the proper g dot ds, which is a scalar for each side. So this is for top, this is, then you integrate over the appropriate limits. So see how this works. For the top, again, right, for this section, we know the value of z, right, it's 1. I've given it here because we are working on the top of the cylinder. Then the rest of it is r goes from 0 to 1, right, the radius is from 0 to 1, and phi goes all around 360 degrees. Okay, so r, which is this, we are looking for the whole area, right, so that goes from 0 to 1, okay, because the radius given is r equals 1. So based on that, if you integrate the surface, you're going to get this value. Similarly, the bottom is pretty much the same thing with a negative value. Yeah, this should be bottom, I'm sorry, instead of T, make sure this is bottom, and this comes out to be this. And then the side, you use this formula, okay, where r is fixed for the sides, and the other two variables go from z equals 0 to 1 and phi equals 0 to 2 pi. And then if you add all this up, you come up with 0, which means that the surface or the field has no source inside the cylinder. Okay, so that's how you solve this problem. Let's move on. Now we come to an example on volume integrals from our textbook, and this is example 3.6. It's on page 147. Okay, so this is a pretty simple example. There's a sphere like a football of radius 2 centimeters. It contains a volume charge density given by this, and he says find the total charge contained in the sphere. So you just apply this volume formula that we have talked about in the past, and you solve. There's not much to this. It's a simple problem. I will let you look through this. Please spend enough time so that you understand the logic and how it's been done by the writer. The one thing that I did want to point out, and that's why I gave you these little notes here, there is and the writer is not explaining this well enough, this particular section. So you run into a situation here where you have to find integral of sine theta to cos square theta. Integral of sine theta cos square theta d theta. Now the answer to this is minus cos cube theta by 3. You may know this, you may be good at integrals. But if you don't, then this is the way to solve it. So I found this somewhere and I put this in to help you along. But it is a triple integral, so it can be a little scary, but I think you will be able to figure it out. Use my notes to understand, but the answer comes out to be 44.68 microcoulombs to answer the question, what is the charge in the sphere? Okay. Alright, so that's one example of a volume integral. I have another example of a volume integral that I picked up somewhere else. So here it says evaluate this triple integral for this function 2x plus y, where V is the closed region bounded by this cylinder. So there's a cylinder and then there are the planes x equals 0, y equals 0, z equals 0, and then y equals 2. So this is an interesting and challenging problem. So let's see how we solve this. So let's go here, the volume integral. So this shaded portion is the surface, okay. So we have to apply this formula with V, the closed region is what I show here. So this is V, this whole thing in a cylinder lying on its side, and it's not an endless cylinder. It is defined very well how big it is going to be. On one side it's hitting the y equals 0 wall. Think of this as the three walls in your classroom, right? There's one wall y equals 0, there's another wall, the floor actually, z equals 0, then there's another wall y equals 2, right? So the three walls act as boundaries, and the fourth boundary is the cylindrical surface z equals 4 minus x square. And then actually there's a fourth wall also, sorry. There's actually 5 boundaries. X equals 0, y equals 0, z equals 0, and y equals 2 are 4 walls or planes. Then the fifth boundary is the cylindrical surface, right? Z equals 4 minus x square. So with all these walls, this is how it looks like. And then once you know that, then it's a quick application of the limits to this formula. And so I've given you some limit notes on what the limits are. For x, y it is 0 to 2, right? So it satisfies this equation only between 0 and 2. It can't be more than 2 because then you hit the other walls, right? So that's what I've tried to explain here. So please go through this. Higher x is not possible, lower x is not possible. So 0 to 2 are the limits. The other limits are pretty easy to understand. So here is the whole expression for the integral. It's split into two parts, 2x and y. So I've separated those, and then if you solve using the methods I've told you on how to do triple integrals and double integrals, first you do the inside, then you do the middle, then you do the outside integral, you should come up with 80 by 3. Okay. All right. I hope that's enough explanation. Please try it. If you run into problems, we can talk. All right, moving on to the last section, the del operator and the gradient divergence and all that. Let's keep moving. Slide 69, 70, 71. Okay, an example from your textbook. This is on page 159, 155. Sorry, I'm losing my mind here. I'm going to 155 on your textbook, and it's a simple calculation of, yeah, sorry, 3.9 is not 150, yeah, page 155. Yes, okay. Find the directional derivative. It's not the gradient itself, but you have to find the directional derivative, and the directional derivative is like this. So you first have to find the gradient, apply del to the t given t value, use the partial fraction method, and then you have to let's see, yeah, so you've got the t, so do the del t, the gradient, then you're given a direction. So first find a unit vector along this direction, which means you take this vector and divide it by the magnitude. So he shows you how to do that in the example. Then you do dt by dl, which is the directional derivative, as again the scalar product of del t, which we just did, and a dot product with the unit vector in the given direction, this direction. So if you do that dot product, you come up with a value, an expression in x, y, z. Then we are given x, y, z a certain point, and if you put these coordinates, you get the value as minus 10 by root 17. So again, take some time, go through this problem and make sure you understand. It's simple calculations. I don't think we need to spend too much time on it. Moving on to slide 72, which is also an example from the textbook, where we have to find gradient, right? And you know the formula for the gradient, we just talked about it, which is just del t or del of whatever is given. This is on page 156 of your textbook. Find the gradient for each of these v's at a certain point, right? Pretty simple. All you have to do is do the partial derivative, then for x, y, z, or whichever coordinate system it is, r phi z or capital R phi theta, whichever, apply those values and you will get the answer. Okay, all right. So I'm going to not spend too much time on that. We have a couple of important ideas too that may take a little more time, and I know we are running short of time. So I'll keep moving ahead. Here is on page 76 is a summary of all the formulas for gradient, divergence, curl, Laplacian in each coordinate system. This is actually in the back, the very last page of the textbook. So that's where you have to go to find it. I copied it here so you have it for ready reference. You'll definitely need this as we solve these problems. Okay, example 311 on page 160. Here we are asked to find divergence. Again, this is a scalar product. I'm not going to go through this in detail. I'll leave it to you to look at. But I'll stop at slide 78, where I'm picking a problem from the back of the chapter, problem 346, to solve. Okay? So we are given a vector field and the surface on which to apply this, we have to find the outward flux, right? Flux means you have to do a surface integral, area integral. But the nice thing is the divergence theorem tells us that you can do flux both ways. You can do it as an integral of a volume, or you can do it as an integral of a surface area. And in fact, we are being asked to prove that both ways of calculating gives you the same value. Okay. Now the surface is cute. It's a cube. So you have 6 sides: top, bottom, left, right, front, back, right? So 6 sides, and it's 2 units each. So from here to here is 2 units, is also given. So given all this information, we have to do these 2 integrals. Okay, so I will show you how I did this. Problem 346, it's here. So there are 6 integrals you have to do on one side, part A, which is the left side. Then you have on the right side, which is the volume integral, you only have to do one integral. But see how the limits have to be defined. And I again don't have too much time to go into this, but the answer is here. And in both ways, you can see that we get a value of minus 8.3 for that total flux. Okay, and we also prove that this verifies Stokes. Oh, sorry, it verifies. We're talking about the divergence theorem. Yeah, it verifies the divergence theorem. Okay, so that's 346. I'll probably skip many things here. Here's an example on determining curl. This is not from our textbook, but I brought it from somewhere else. You can see how if you're given XYZ coordinates in this way, a non-uniform vector, then how you do the curl calculation, and at a certain point, how do you derive the actual curl. Okay. Stokes theorem also is something we need to become comfortable with. Stokes theorem gives us a relationship to find a surface integral, but the surface integral, which is an integral on a curl, can also be derived by a line integral, right? So both are the same thing is what Stokes theorem tells us. So your problems are going to tell you verify Stokes theorem by solving for something using this method on the left and then using the right integral on the right, and your value should be the same for both. Okay, so here's one problem I did, not from our textbook, from somewhere else, but here the surface to use for the left side is this top cylindrical surface. To derive the bottom or the right side integral, the line integral over a closed path, that C is just the boundary, the bottom circle. So knowing that, if you carry out the integration, it works out to be the same. Okay, so this is verify Stokes theorem. So go through the steps yourself. You get an answer of the value of the integral is pi on the right side, and then you do the surface integral, you get pi, so Stokes theorem is verified. Okay. We got a couple more problems. Please bear with me. I know we are over time. So here's Stokes theorem from our textbook, a problem 355. Here we are given this path. It's on the x and y axis only, right? Nothing in the z axis. So again, you have to do two integrals, one a line integral and one a surface integral, and prove that they are equal. Okay, so I've given you some formulas here so that you can apply them, and I've solved it here, 355. Please go ahead and walk through this, and if you have any questions, ask me or talk to your co-faculty, but make sure you understand exactly each step. Okay. The remaining problems are pretty easy. They won't take too much time. They're just easy mathematics. So this is actually to say whether a field is solenoidal or conservative, and what that means is if you calculate the curl as this, as a cross product, and if it's 0, then you say it's a conservative field. If you calculate the divergence, which is a dot product, if it's 0, you call it solenoidal, and I show you how to, the calculation itself shouldn't be too difficult for you also. Last topic is a Laplacian. We have one problem from the back that I've solved, so you can look that up. I also give you, actually both of these are not in the textbook. There is one example in the textbook. I think you can look that up. If not, you can see how the Laplacian is done. Remember, you're given a V, and the Laplacian involves two partial differentials, right? So first you do the first partial differential with respect to x, with respect to y, with respect to z of the given V. Then you do that a second time for each of them, and you finally get a value for del square V. Okay, so here's one that I've solved, and I've also solved one here, problem 358 from the back of the textbook. Sorry, that is actually slightly ahead. Yeah, 358. So 356 came after 358. I apologize. So on page 17 of my PDF, here's another calculation for the Laplacian, and that comes out to be this value. Okay. All right. I know this was a bit rushed, but I warned you in the beginning. They've not given us enough time, so we are going through this at high speed. But you should take all the time you want to sit through each one of these work problems, to sit through the examples, make sure you understand each one, and also do the homeworks by yourself so that you totally get the material. Okay? Thank you.